Hello everyone, it's Mahdi and today I want to present Lunar Concrete as a final term project of C436 course instructed by Professor Alexandra Adlenska. To start with, you've probably heard of Artemis program designed by NASA with the goal of returning humans back to the moon. But why do we want to do that? As human beings, we have this never-ending desire to explore outer space ever since we know its existence. Since the moon is the most familiar and the nearest extraterrestrial body to us, it's scientists and engineers' first target to know more about outer space. Moreover, some see the moon as the potential source of valuable resources. Extracting resources from the moon could potentially support future space missions and even provide resources for the use on Earth. And also, we have to go there to establish a human base on other celestial bodies. But why do we want to do that? This could probably provide a backup for humanity in case of any catastrophic events on Earth. It can also serve as an ideal test platform for human beings to utilize the moon's rich resources and perform scientific explorations. Also, if you want to explore outer space more effectively, it's necessary to utilize in situ resources instead of returning back to the Earth each time, which could reduce overall space exploration costs by a factor ranging between 10 to 50 times. According to NASA's Artemis project plan, to give astronauts a place to live and work on the moon, the Artemis base camp includes a modern lunar cabin, a pressurized rover, and a mobile home. To have an estimation about this plan's cost, it should be noted that the estimated cost of establishing a human base camp on the moon can vary significantly depending on numerous factors, including the scale of the base, technological advancements, and infrastructure requirements. But if you want to deal with numbers, I can say that according to the latest updates, the Artemis program was projected to cost around $28 billion for the initial phase, and in a workshop that took place in the August of 2014, representative from NASA declared that this permanent base is going to cost NASA around $10 billion. Before jumping into the concrete for use as extraterrestrial construction material, we should know the conditions that this material will undergo. Moon's environment is a very harsh one, and this hostile environment is unfavorable to human life and to the materials as well. First off, lunar atmosphere is very thin, so it can be considered as a vacuum environment with no special protection against meteorites. Severe vacuum conditions cause materials to release volatiles which accelerate material deterioration. Second, each day on the moon is equal to around 27.3 days on the Earth, and the temperature varies significantly during this period from 150 degrees of Celsius during the days to minus 180 degrees of Celsius at midnight, which will enforce us to use a material with an excellent heat and cold resistance. Furthermore, even though low gravity of moon alongside the absence of tectonic plates reduce the dead load of objects and causing significant moonquakes, it can adversely influence the materials formation and its fundamental processes such as microstructural development. Moon surface is also covered with a layer of loose granule, which is referred to as regolith. An analysis run on NASA collected samples demonstrated the high silica and alumina content, as well as moderate presence of calcium oxide in the moon's soil. Also, sulfur can be found on the moon, mostly in the form of FeS. The first motivation to use concrete in the moon rises from the fact that raw materials of cement, such as silicium oxide, could be obtained from the moon. Accordingly, looking from economic point of view, a concrete may be the most suitable material for lunar construction. Moreover, our wide knowledge about behavior and design of concrete structures for extreme conditions such as nuclear power plants and concrete's ease of shaping and fabrication and overall mechanical and durability characteristics, which I will elaborate a little bit more on them in the next slide, made it a suitable choice for extraterrestrial construction. However, water demand of cement particles for hydration is a challenging issue when it comes to use concrete on moon. As a result of these studies, modified concretes has been suggested to be used on the moon surface. Some of them are calcium aluminate concrete, sulfur concrete, magnesium silica concrete, polymer concrete, and also geopolymer concrete. In what follows, I will elaborate on specifically geopolymer concrete, which demonstrated to be a suitable choice for lunar construction. Geopolymer concrete is formed as a result of a reaction between aluminum silica rich base material, which can be obtained from silicium oxide and alumina in the moon's soil, and alkaline reagents, which can be obtained from alkali metals on the moon, as well as aggregates that can be obtained from regolith. The main reasons for high attention toward using geopolymer concrete for lunar constructions are that they have low water consumption, they have high size stability even at high temperatures, and good vacuum stability, and they also have this ability to resist extreme temperature cycles. However, geopolymer paste mostly have very high viscosity, which can cause workability issues and also it forces us to use high shear mixing. Additionally, it's been observed that conventional water reducing admixtures are not as effective on this type of concrete or as compared to a normal type of concrete made of cement. So some other admixtures should be developed to increase workability of these materials. The rheology properties of geopolymer concrete on Moon becomes even more important as we know that 3D printing techniques should be used. So we should look for other superplasticizers. As strange as it sounds, recently urea has turned out to be a suitable option which can make buildable and workable geopolymer structure. Why is that? First off, it can be easily obtained whenever humans are present even on the Moon. Additionally, longer setting times after using urea can help us maintain a continuous flow during 3D printing process. And it was observed that using urea results in higher level of geopolymer gel formation during extreme temperature cycles. However, the compressible strengths of samples made with this test will drop up to 50% under vacuum conditions. One of the main advantages of using geopolymers is that they can gain high strength level at early age. Additionally, Jung et al. Showed that this extreme high and low temperatures had insignificant effect on compressible strengths, whereas geopolymers can have compressible strengths of 50 and 80 megapascal under exposure to 120 and minus 30 degrees of Celsius. The study of Alexidius et al. Also proved that lunar geopolymer concrete can gain a flexural strength of around 14 megapascal, which is higher compared to that of or OPC concrete that we are using on Earth. In terms of durability, a study of Zhong et al. Demonstrated that after 40 cycles of extreme temperature cycles from minus 196 to 25 degrees of Celsius, the compressible strength of the geopolymer samples even increased. Moreover, Montes et al. Showed that geopolymer concrete with a moderate density and thickness between 500 to 1000 millimeter can offer adequate protection from radiations on the Moon. There are contradictory results regarding the effect of vacuum condition and compressible strength of geopolymer lunar concrete. Interestingly, Zhou et al. Also found that curing geopolymer under vacuum conditions can even favor their compressible strengths due to the absence of efflorescence effect. Before we wrap up, I want to point out the reference slide at the end of the presentation. It contains a list of sources that I use for this project. And many thanks to the Moon and Back for your time and attention. And please feel free to reach out with any questions or concerns, whether through in-person meeting with me at my office or through email.